Chapter 6, Memory. We all know that how important is memory in computer circuits. Without memory, of course, there is no way to there is no way to put a processor in work, and the processor cannot operate because the processor needs the memory to get the data from the memory and execute the data and perform some functions. Okay, so we need memory, and all of us know that we have different kind of memories. We have fast memories, small memories. We have big memories, slow memories, and we have a very fast memories like next to the processor and that. So let's just talk about all those memories one by one. So let's first see what is the objectives of what are the objectives of this chapter. So we want to be master and learn the concept of hierarchical memory organization. Hierarchical means that like memories are in a hierarchy and from slow to fast or from small to big memories. And we want to learn how each level of memory works and how it can be contributed to the performance of the system, and of course how we can measure the performance. Without measuring the performance, of course we don't know how to like represent the performance of each memory. So we need to learn and know a way to measure the performance. Okay, and of course we want to know what is like what concepts are behind different types of memories, like such as cache memory, virtual memory, memory segmentation, paging, address translation, and of course memory mapping, which is missed like in this part, memory mapping. Okay, so here is the introduction. Of course, we know that the memory is heart of the stored program computer, and we in the like chapter 3 we learned how to build a memory using flip-flops. If you remember, I said that each flip-flop can store 1 bit of data. So if we have a like 16-bit memory each, like sorry 16 byte memory, so we should say 16 byte, each byte is 8 bits, so 16 times 8 uh flip-flop we need to build a 16 byte memory. And we now we will learn the memory organization in this in more detail in this chapter, and we will learn how to analyze the system performance. Okay, so the first thing first, there are two kinds of memory. We have two different types of memory, not just two types, just kinds. They're like the big picture. The big picture, we have two kinds of memory. We have a RAM memory, we have a ROM memory. RAM memory is a random access memory, and the ROM memory is read-only memory. Okay, so we have the two kinds of main memory, which is RAM, random access memory, and it is RAM, read only memory. Okay, and the RAM itself has two different types. We can have dynamic RAM, which we call it DRAM, and we have static RAM, we call it SRAM. Okay, so before moving to DRAM and SRAM, let's see what is different between a RAM and the ROM. RAM, in fact, is a memory that we can access to any address location independently, and the like the main feature of the RAM is that it keeps the data as long as it has power. Okay, as long as it's connected to the power supply, it keeps the data. If we turn off the power, remove the power, the memory will be wiped out, and so there is no data in the RAM. But the read-only memories are kind of those memories that even after disconnecting the memory from the power supply, they still keep the data. Okay, and we are able only to read from those memories. We are not able to write on those memories. Of course, there are different methods to write data in RAM, but it's not like a write signal which we apply. Okay, I want to write this data to read-only memory. No, we cannot do that. There are different methods. We need to separate the chipset from the board and fill it with the data and then connect it to the board. And now it keeps the data forever. Okay, and so we can only read the data from the read-only memory, like a BIOS of a processor. Each computer has a BIOS. If you look the BIOS has like basic booting information of the processor and the computer, and the data doesn't erase even after you turn off and unplug the computer from the power. So the power is always in the RAM. I have a question. It holds instruction, right? Yes, it can hold instruction and data, both of them. All of them, we call it data because there are information. Some of those information are like in instruction form. Some of the data are in data form, like the uh, operands. Okay, but no matter what kind of data it is, instruction, it is it is data or instruction, keep all data. Okay, so the as I mentioned, we have two types of memory. It's RAM and ROM, and the RAM itself uh, has two types. We have D and SRAM. And by the way, today, if you can find DDR4, DDR5, like the new generations of DRAM. What is the difference between DRAM and SRAM? First, let me tell you what's the difference between DRAM and SRAM. SRAM, first I want to talk about the SRAM. SRAM is like what we discussed in chapter 3. SRAM consists of circuits similar to the D flip-flop. Okay, so what we saw in chapter 3, which we had D flip-flops, and we combine them, we cascade them, and we build memory registers. All of them are SRAM. But what is DRAM? DRAM consists of capacitors instead of like those those gates in a flip-flop. We have 4 gates in the flip-flop which have feedback and retrieve the data. We use a capacitor. We charge and discharge the capacitor. When we charge the capacitor, it is represents 1. When we discharge the capacitor represents 0. Okay, and by the way, the capacitor slowly leak their charge. So when you charge a capacitor, it doesn't keep the charge forever. The capacitor slowly discharges. So we need to refresh it every few milliseconds to prevent data loss. So if I if we assume this one is a graph, it's time, and it is a voltage of a capacitor, and the capacitor has a voltage of 0. It means it's the logic 0. When we charge the capacitor to 1, it means that the data is 1. But after why the capacitor starts to discharge. Okay, start to discharge and return to zero. So we're losing the data after like a few milliseconds. So what we need to do for a DRAM, so we need to charge the DRAM after a few milliseconds, again charge it. After a few milliseconds, again charge it. So like it's the way we keep the data on default on DRAM. So every few milliseconds, we need to recharge the capacitor. Okay, but we don't need to do that in SD flip-flop because as you remember, I said that in SDRAMs, which consist of flip-flop, the flip-flops keep the data. Okay, what's the advantage of DRAM compared to SRAM? The advantage is here. It's cheap. Okay, it is cheap, so it's not expensive. So like you see that in the like new computers and always they use DRAM for memory. Okay, not SRAM. They use SRAM for very small memories in cache and like registers, but for main memory we use DRAM because it is cheap and we can use it. Any question? If you have any question, you can unmute your microphone, ask me, or you can just type it. Okay, so let's move to SRAM. SRAM consists of circuits like similar to the flip-flop, which we know how do they work, and it is very fast. Okay, it's very fast. And as I mentioned a few minutes ago, it doesn't need to be refreshed. Okay, so it's good. It doesn't need to be refreshed. But what is like disadvantage of this RAM? It is like more expensive, and we need to like pay more to buy SDRAM compared to DRAM. Okay, but still we use SRAM to build cache memory because cache memory needs to be very fast. And so it's the reason why we use SDRAM for cache memory. Uh, mm, okay, so this line talks about the ROM memory, read-only memory. It says it does not need to be refreshed. Of course, it doesn't. And of course, the last sentence, which it's mentioned, RAM is used to store permanent or semi-permanent data that persists even while the system is turned off. It keeps the data even if the system is turned off. Okay, it doesn't like do erase. The data won't be erased after turning off the system, and this like is for read-only memory. Okay, any questions? Okay, now that we know what is SRAM and what is DRAM, and what is RAM, let's move to the next slide and see what is a memory hierarchy. Okay, memory hierarchy, like it's like different levels of memory. Generally, faster memories are more expensive than slower memory. We knew that. Okay, faster memories are more expensive, and of course, small fast storage elements are kept in the CPU. This line it says that fast storage units like registers and cache are kept in the CPU, but like the slower memories like main memory and external storage units are accessible by the data bus. They are like connected to the system uh, through data bus because as I mentioned, we know that they are slow and that's fine. We still have fast memories inside the processor which we can access quickly to them. Okay, so uh, here is a memory hierarchy, which is very important, and different levels. The fastest memory we know, the fastest memory is the register. The register is the fastest memory, which is like inside the processor. Okay. After register, we have cache memory. Cache memory, I said that are small memories that are located next to the processor. Let's show it with dollar sign. So, which is next to the processor. Why next to the processor? Because we want to access the data very fast and we need to keep them as close as possible to the memory. Okay, so we have two different level of cache. We have cache level 1, cache level 2, and of course we also have cache level 3, which is not in this hierarchy. So cache level 1 is smaller than cache level 2, okay, but more expensive, and it is closer to the CPU, and it's faster. Cache level 2, so it's L2, it's L1. Cache level 2 is still very fast, but not as fast as cache 1, and not as close as cache L1, okay, but still much more faster than main memory. Let's see about what's the access time. If we look to access time of the register, we see that any register can be accessed in less than 1 nanosecond. So from zero point 0.3 nanoseconds up to 2 nanoseconds, it takes for the processor or data path to access the data from the registers. Okay, so very fast. Let's say 1 nanosecond. Very fast. So 1 nanosecond is like 10 to the power of negative 9. Okay, so in each seconds we can access the registers around 1,000 million times. Okay, so very fast. The cache level 1 has access time of I by the way, I will post this slides on Sakai tonight. So cache level 1 is still very fast. It's not as fast as registers, but it's not bad. It's like 2 nanoseconds to 8 nanoseconds. Cache level 2 is still very fast, but as not as fast as level 1. It takes 6 nanoseconds to 10 nanoseconds. Okay, after we like move beyond registers and cache memories, the fastest memory is main memory. Okay, is main memory. Main memory like is like a RAM, SRAM or DRAM which we have, and those memories are also fast, and it takes 10 nanoseconds to 70 nanoseconds. Okay, all these four memories are called system level memories. Okay, all of them are called system level memories. By the way, if you look to this hierarchy, you see that when we go to upper levels, the size of the memories are smaller, and when we go to lower levels, the size is larger. On the other side, when we go up, there are more costly. When we go down, there are less costly. Okay, so this one is like how the different level represented in this hierarchy. Okay, after main memory, we have a solid state disk. Okay, solid state disk, like which is a secondary memory. Oh, not here. So solid state disk. And after you see now we moved from nanoseconds to microseconds. So why it's here is very important. It shows that just moving one level down decrease the speed like in the factor of 1,000. because in main memory the access time is like 10 nanoseconds, 70 nanoseconds, and when we move to solid state disk, the access time is 35 microseconds up to 100 microseconds, and we're losing like the speed. How much? Like with a factor of 1000. It's very like um, important. So we should try to keep the information as much as we can in the main memory, the information that we need, because we know that the secondary memories are very slow. And one of the reasons why they are slow, because by the way, because there are kind of outside of the main board. So if they are not directly connected to the main board, which has the memory. And in the other level, we have a fixed rigid disk, and slower than disk, we have optical disk, DVD, CD, and slower than optical disk, we have magnetic tapes, and in the like last levels we have USB flash drive, and we have a removable hard drive. So you see that USB flash drives and the removable portable hard drives are slowest memories. And this, if we want to extend this hierarchy like this, one more level, can you tell me, who can tell me which level we will have on the removable hard drives? Can you guess? Any idea? Just think about it. What is like the source
Would
of the? Go ahead, go ahead.
would it be kind of like cloud storage or something like that?
Exactly, it's the cloud storage. Exactly, very good answer. The cloud storage, like Dropbox, Google Drive. Okay, so all those cloud storages are like, even still there are storage, but they are super slow. Okay, compared to that. Okay, so and so we see that the storages are also the below the removable hard drives and so on. Any question? I got one answer. It's like offline bulk memory. It could be, yeah. But offline bulk memory, I think you mean cloud memory, because offline bulk memory is like memories in the server that are stored in somewhere in database like Google, and we access those information by like internet. It's the same. Okay, I got the like confirmation. So by the way, there is still kind of cloud storage. How long does cloud memory take to access? It's the old name for it. Okay, that's why. Just the question I got here: how long does cloud memory take to access? It depends to your internet speed. Okay, so see what is your internet speed. You have like 1 megabit per second, so you can access 1 megabit of data per second. It depends how fast is your internet connection, and of course, what's the bandwidth of the data transformation. Okay, so it depends to both the bandwidth of receiver and sender. What if we have a LAN storage on a separate PC? Is that cloud storage? What if we have a LAN storage on a separate PC? It's a like a question. I would say uh, cloud storage. If you have a LAN storage on a separate PC, it's not a cloud, because the cloud. If you mean the cloud is something that you can access it from anywhere, you know. if you have like an internal network, Ethernet, inside the like complex, inside the like center, that you can access those data from the center. Let's say we have an internet at Shepherd, and let's say we have an Ethernet at Shepherd. So the Ethernet at Shepherd is a like a network that we can access only from the Shepherd, not from the outside. So it's called a local cloud. It's not like a general cloud. But what I mean from the cloud, I mean the like information databases that can be accessed from anywhere in the world. Okay, and as so the same question asking me if like a network drive can be counted as a cloud. I would say we cannot call it cloud. It's like local storage. It's not cloud because cloud means that something that we can access from anywhere, anywhere in the world. Okay, not from like inside the organization. Okay, so yes, of course. The question says, so cloud storage means it must be connected to the www. I think so, yeah. The cloud is something that is available for everyone. But have, we might have some local cloud. So we have a very big organization, very, very large organization. They built like a local cloud for themselves and they give it the name. But in general, yes, you're right. The cloud storage means that it must connect it to like the internet and it can be accessed from anywhere. Anywhere. Okay. Any question? Any other question? Okay. So very good. So let's move to the next slide and discuss the memory. Okay, so what we are like most interested in this class in memory hierarchy, we interested in registers, we interested in cache, we interested in main memory, and of course virtual memory. Okay, so we're not going to discuss clouds like solid state memories and different type of external storages. We are interested in registers, cache, main memory, and virtual memory. And of course, registers that I mentioned, there are locations that are inside the processor itself. And what is the virtual memory? We will talk about the virtual memory later. But what does virtual memory do? It, in fact, it extends the address space from the RAM to the hard drive. Okay, so it means that if we have if we have 4 MB of the like a RAM in Mali processor, and if you remember, for not for in Mali processor we have 4 kilo. So if we have 4 KB of RAM in Mali processor, it needs 12 bits to address like this 4 kilo. But what if our program is very big and it needs 8 kilobits of like a RAM? So we keep 4 kilobits of of the program inside the RAM and other 4 kilobits inside the like hard drive. And by using virtual memory, we okay, I see. You see now. 4 KB in the RAM and 4 KB in the hard drive, and we behave with both of them as a like RAM memory. So we assume that our RAM is 8 KB instead of 4 KB. How we can do that? By using virtual memory. We extend the address space for the RAM. Okay. So here is it. So using virtual memory, we can extend the address space from RAM to the hard drive. So we can just consider hard drive as a part of the RAM and like in addressing. Okay, we will discuss virtual memory later. but here it was just an introduction. And this line says that virtual memory provides more space, of course, because we're extending the address space, and cache memory provides speed. So it's the difference. What's the difference between cache memory and virtual memory? We can say cache memory provides speed and virtual memory provides space. Okay, any question? We will discuss virtual memory and cache memory like later in this week and next week.